Hello friends and welcome. Today we will be discussing about margarine. The objectives of today's lecture are: first, to get acquainted with the basics of margarine and explain its manufacture and properties. Second, to study the composition of margarine, and third, to briefly discuss the types of margarines manufactured. Let us first have a look at what margarine is. Table margarine is made from appropriate oils and fats such as soybean, rape, canola, cottonseed, palm kernel, coconut, which may have been fractionated, blended, hydrogenated in varying degrees and or interesterified. Fish oil may also be included. Other ingredients include surface active agents, proteins, salt and water along with preservatives, flavors and vitamins. Margarine production involves three basic steps: emulsification of the oil and the aqueous phases, crystallization of the fat phase and plastification of the crystallized emulsion. Water and oil emulsions are cooled in scraped wall heat exchangers, during which time fat crystallization is initiated, a process known as nucleation, and during which the emulsion drop size is reduced. There follows a maturing stage in working units during which crystallization approaches equilibrium, though crystallization may continue even after the product has been packed. Fats usually crystallize in two different forms known as beta dash and beta. Of these, the beta form is thermodynamically more stable and will therefore be formed in many fats and fat blends. For margarines and other spreads, the beta dash form is preferred since the crystals are smaller, are able to entrap more liquid to give firm products with good texture and mouthfeel, and impart a high gloss to the product. Beta crystals, on the other hand, start small but tend to agglomerate and can trap less liquid. It is therefore desirable to choose a blend of oils which crystallize in the beta dash form. Margarines and shortenings made from rapeseed or canola, sunflower and soybean oil after partial hydrogenation tend to develop beta crystals. This can be inhibited or prevented by the incorporation of some cottonseed oil, hydrogenated palm oil, palm olein, tallow, modified lard or hydrogenated fish oil. All of it stabilize crystals in the form. The canola, sunflower and soybean oils all have high levels of C18 acids, while the remaining oils have appreciable levels of C16 acids or other chain length along with the C18 acids, and thus contain more triacyl glycerols with acids of mixed chain length. It is not possible to list all the formulations used to make margarines, and the following examples are merely indicative. In the following blends, hydrogenated means partially hydrogenated. Blends of hydrogenated soybean oils with or without unhydrogenated soybean oil. Blends of canola oil, hydrogenated canola oil and hydrogenated palm oil or palm stearin. Blends of various hydrogenated cottonseed oils. Blends of edible tallow with vegetable oils such as soybean and coconut. Blends of palm oil with hydrogenated palm oil and a liquid oil such as rapeseed, sunflower, soybean, cottonseed and olive. Palm oil about 60%, palm kernel oil 30% and palm stearin 10%. Palm stearin about 45%, palm kernel oil 40% and liquid oil 15%. For hot climates, a harder formulation is required, as are the last two examples from Malaysia. Margarine is expected to have a shelf life of about 12 weeks. With good ingredients and absence of pro-oxidants such as copper, oxidative deterioration is not likely to be a problem, but care must be taken to avoid microbiological contamination in the aqueous phase. This is avoided by hygienic practices during manufacture. The addition of some salt about 8 to 10% in the aqueous phase, corresponding to a little over 1% in the margarine, control of pH of any cultured milk that may be used, and careful attention to droplet size in the emulsion. Margarines are now available with added phytosterols, which it is claimed are able to reduce blood cholesterol levels. Now, let us see the structure of margarine. Margarine is an emulsion of the type water in oil, consisting of 80% fats and oils and 20% of an aqueous phase, which, like the oil phase, contains soluble ingredients. About 20% of the triglycerides of the fat blend are solid at room temperature. The remainder is liquid. During processing, a phase inversion takes place in the emulsion, so that in margarine, water is the dispersant, oils and fats constitute the continuous phase. That means that water is dispersed in droplets in a continuous oil matrix. The oil phase of margarine as well as the structure of process shortening is not homogeneous, but consists of a network of fat crystals and of agglomerates of fat crystals with liquid oil distributed in between. Margarine draws its mechanical stability from the crystal network as well as from the stability of the emulsion. To achieve a certain consistency, the crystal networks built often have to be destroyed intentionally by overworking. By agglomeration of crystals, stability is regained. Crystal growth continues after the product has been processed and wrapped or filled into tubs. The margarine matures and stiffens up. Now, the composition of margarine. Margarine contains 80% oil with 40% in the half-fat margarines or margarines that were first introduced in 1964. In some countries, this amount can be chosen deliberately. The oil phase contains the fat-soluble ingredients. These are usually fat-soluble flavors, vitamins, as well as emulsifiers and carotenes. The aqueous phase holds the water-soluble ingredients, which are generally water-soluble flavors, salt, milk or milk solids, and in special cases preservatives. Fat blend. The choice of the fat blend of margarine follows 3 criteria, namely the achievement of certain physical properties, the presence of claims or declaration on the pack, and nutritional physiological considerations. At present, animal fat has almost completely disappeared, and vegetable oils and fats are dominant in almost all countries. The fat blends are composed in such a way as to yield a certain consistency at a given temperature. The solids content at that temperature is the measure. Then, emulsifiers. Emulsifiers stabilize the emulsion. The main emulsifiers used are lecithin and monodiglycerides. Lecithin replaces the egg yolk that was the only emulsifier in margarine in the old days. Monoglycerides and monodiglycerides are naturally associated with oils and fats. They can be reduced by the reaction of fats and oils with glycerol. The surface active properties that stabilize the emulsion are due to the hydrophilic properties of the glycerol OH residue and the lipophilic properties of the fatty acid chains of the ester. Monodiglycerides have a melting point that lies 10 to 20 degrees centigrade above the melting point of fats and oils that are composed of the same fatty acids. Therefore, during cooling, they crystallize early on in their position around the water droplets between the water and the oil or fat phase. This creates additional stability. The suitability of the emulsifiers for certain types of emulsions can be described by the HLB value, which is the hydrophilic lipophilic balance. After this, the milk components. In some countries, milk components are prescribed as ingredients. Most margarines contain milk solids. The finely dispersed proteins and lactose bind boiling nuclei when the water is evaporated from the melted emulsion. This decreases spattering. In addition, all milk components that have passed a souring step carry flavors, traces of butyric acid, ketones, lactones, as well as diacetyl and its precursors. These substances work as flavors on the one hand, and at the same time they mask off flavors that arise during long storage of the margarine. Milk proteins also reduce the tendency of the fat to oxidize during frying. Acids. Acids have to fulfill several tasks. On the one hand, they lower the pH value, improving bacteriological stability. In addition, they create a better, fresh taste. The use of lactic acid gives a peaked, fresh taste. Salt. Salt has two functions. One is to decrease the microbiological sensitivity, the other is to act as a flavor. Sodium chloride is the commonly added salt. However, potassium chloride can be used in sodium-free margarines. Flavors. The flavors used depend on the geographical region, that is, the local taste, and can range from bland to over buttery to cheesy. If butter is normally slightly rancid in the respective country, this can also be reflected by the flavor notes used. Dosage also is done according to local preference. Many synthetic butter flavors are also added in margarine. They are usually based on mixtures of compounds that have been identified as contributing to flavor of butter, such as lactones, butyric fatty acid esters, ketones, and aldehydes. Now, preservatives. Preservatives are rarely used in 80% fat margarines in countries with moderate climate, households equipped with refrigerators, and well-developed logistic chains. In reduced fat margarines, they are not necessary for production, but are needed to protect the product during open shelf life. Margarine preservatives fall into three categories: antimicrobial, antioxidant, and metal scavenger. Antioxidants are necessary for the oxidative stability of products formulated with meat. Vegetable oil margarines usually don't require antioxidants, as the tocopherols present in them act as antioxidants. Scavengers such as ethylene diamine tetraacetic acid, written as EDTA, isopropyl citrate, etc., tie up or chelate trace metals that act as catalysts in oxidation. Some principally used preservatives in margarine are benzoic acid. Benzoic acid is added in a concentration of less than or equal to 0.1%. It works as a preservative in the undissociated form only. The working mechanism of benzoic acid is based on the inhibition of enzymes belonging to the acetic acid cycle. It also inhibits oxidative phosphorylation as well as the citric acid cycle and has a negative influence on cell walls. Sorbic acid. Sorbic acid usually is allowed up to 0.12%, but the amount used is normally lower. The working mechanism of sorbic acid is based on the inhibition of enzymes of the carbohydrate cycles and the citric acid cycles. Sorbic acid forms covalent bonds with SH group of the enzymes, thus inactivating them. In addition, it has negative influence on cell walls. Then, thickening agents and stabilizers. In half-fat margarines or margarines with an even lower amount of fat, the emulsion on its own is no longer able to stabilize the product. Therefore, thickening agents or stabilizers, for example gelatin, are used to stabilize the water phase. Next, colorants. In Europe, margarines usually are not colored with artificial colors. Often, however, beta-carotene is added. It dissolves in the oil to give a reddish color. In many countries, Bixin and annatto are allowed in margarines. Vitamins. Usually, fat-soluble vitamins A, D, and E are used. In geographical regions with deficiencies in water-soluble vitamins, some B and C vitamin addition is also common. Margarines should not contain less than 15,000 international units of vitamin A per pound. Addition of vitamin D is optional. When added, should be about 1500 international units per pound of margarine. Water. Water usually stems from wells on the margarine factory sites or it is taken from the municipal net. Water quality must be monitored constantly. Air and nitrogen. Some margarines and fats are whipped with nitrogen or air to soften the products. These are called the so-called soft margarines. Let us now have a glimpse at the physical properties of margarine. Margarine is plastic, which means that its internal repulsive forces are not sufficient to bring it back to its original shape when it is deformed under outer pressure. Because the inner structure of margarine can be softened under mechanical influence, example kneading, the structural bonds are then destroyed so that only the molecular bonds between the crystals stay in place. Hardness and flow limit of margarine are closely connected. Heart health margarines with a guaranteed high amount of polyunsaturated fatty acids are much softer than other margarines due to their fatty acid composition. Hardness of margarine is determined by many factors. If it crystallizes in the pack, that is after production, this results in a much harder product because the margarine can no longer be overworked mechanically. The lower the oil content, the harder the product. Primary bonds between the crystals stay intact even during mechanical overworking. Secondary bonds are broken up. Strong primary bonds therefore contribute greatly to hardness. The higher the shear stress during overworking, the more the continuous structure turns into a grainy structure. Air or gas, whipped in intentionally or unintentionally, also influences hardness. Proportional to the amount of gas, the number of crystals per volume decreases, margarine becomes softer. By comparison, for butter, churning leads to an air content of 5%, soft margarines contain 10 to 20% air or nitrogen. Now coming to margarine production. Production of margarine consists of some principal steps starting from refined oils and fats. These principal steps are shown in the figure. Apart from the fat blend, the properties of the finished product are rarely influenced only by steps C and D. The composition of the ingredients has only a minor influence. Post-hardening after packaging cannot be influenced and is based on the properties that are inherent from steps C and D. Now looking at the steps. First, ingredient preparation. There are two extreme variations in the way that ingredients are prepared and added. On the one hand, it is possible to prepare single aqueous or oily solutions of single ingredients and then blend them with the fat blend, the water and the milk by means of a multi-head proportioning pump, which is known as the proportioning process. Static mixers built into the tubes then emulsify the mixture. On the other hand, the complete margarine composition including fat and water phase and all ingredients can be mixed in one batch, from which the emulsion is then directly processed through a scraped surface heat exchanger, which is known as the premix process. In between these two extremes, all intermediates of ingredient and emulsion preparation are possible, and there are examples in the industry for all of these intermediate steps. Next, milk souring. As a source for the production of soured milk, pasteurized fresh milk or milk that is reconstituted from milk powder and water is used. The milk is pasteurized and soured with cultures such as Streptococcus lactis or Streptococcus cremoris. Souring can be carried out with parts of a mother culture that is inoculated or by using deep frozen or freeze-dried cultures purchased from a third party. Souring itself also follows this pattern. Ripening of the milk takes about 12 hours. The soured milk is stored in hygienic, cooled batches and transported via a piping system. Water-soluble ingredients. The water-soluble ingredients such as salt, preservatives and water-soluble flavors are prepared singly or as a mixture. Usually they are rinsed into the storage batch by circulation over a venturi tube or collected from mother solutions. Such solutions can also be purchased as such, for example, brine. Oil-soluble ingredients. These include lecithin, mono and diglycerides, vitamins and, to some extent, oil-soluble flavors. Oil-soluble ingredients are dissolved either in a single oil or in the relevant margarine fat blend. In both cases, the amount of fat from the prepared ingredients has to be taken into account when calculating the total composition. If 1 oil margarines, for example, sunflower margarine, are produced, the oil for dissolving the ingredients must be the same oil as for the margarine unless legislation allows for a certain amount of foreign triglycerides. Oil or fat blend. There are two principal possibilities for preparation of the fat blend. One is to blend fully refined oils and fats, the other is to compose the blend from crude oils and to refine the complete blend. Of course, it is also possible to combine both alternatives, which means blending fully refined oils and fats with fully refined fat partial blends. The assembly of the oil in a batch is done gravimetrically over a composition weigh scale or volumetrically over a rotary piston meter or a mass flow meter. Bacteria cannot grow in the oil-fat composition. It is therefore not necessary to pasteurize the oil blend. Pipes should be flushed regularly with hot oil to remove the fat sediments on their walls. In fact, it is important to exclude water from these vessels and pipes to maintain quality. Emulsifying. To emulsify the oil and water phases, they have to be mixed carefully. Depending on the process chosen, this is done at least partly in the premix batch or later in the proportioning pump. Usually, additional static mixers built into the pipes complete the task. Emulsifying is easily accomplished because all margarine compositions contain sufficient emulsifiers that support it. At first, an emulsion of the type oil in water is built. This is converted by phase inversion into an emulsion water in oil, cooling or crystallization and working of the emulsion. To achieve the desired consistency, the margarine fat oil blend must be properly composed to achieve these properties. Within the given limitations of the specific fat blend, the consistency of the margarine can be heavily influenced by processing. In principle, processing is a sequence of cooling steps that start crystallization at different temperature levels, that is, holding zones that allow for further crystallization without cooling and application of mechanical stress to break up secondary bonds to the degree desired. Heat has to be deducted as well to cool down the emulsion and to remove heat of crystallization. Fats and oils crystallize relatively slowly, some very slowly. If slowly crystallizing fats such as palm oil at 60 degrees centigrade are set in a bath of 0 degrees centigrade and are cooled down, it takes up to 2 hours until they are fully crystallized. Packing. Today, margarine is immediately packed after it has left the processing unit. The packaging material's task is to give optimal protection to the product during transport, shelf life and use. For household margarine, an appealing design would improve sales promotion. In addition to the mechanical protection that the product needs as it leaves the processing unit in a soft state, protection from light and oxygen is necessary. Beyond that, the packaging should be as watertight as possible to prevent the margarine from drying out. Surface water evaporates from the product until the head space between product and packaging lid is saturated. If the pack is tight, drying out is low. If not, water vapor can escape the pack so that it evaporates more and more from the product surface. A dark yellow surface, the characteristic color of the dried out fat phase, remains. Special margarines. Margarines for special purposes differ in their properties of use, characterized by their C value and their solids content. C value gives an idea of the hardness or softness of the margarine. Usually it ranges from 100 to 1500 but could be higher. Margarines with C value less than 100 are not spreadable as they are too soft and flow away. A C value of greater than 1500 designates margarine that is too hard and difficult to spread. These include cream margarine. Usually cream margarines have low melting points, about 30 to 34 degrees centigrade. They are used for cake fillings and decoration and must be whippable. That is, hold the air whipped in, which is achieved mainly by the enormous number of fine crystals. Bakery margarine. Bakery margarines have a higher melting point, about 35 to 38 degrees centigrade, than those products produced for direct consumption. They do not have to melt in the mouth, but are designed to separate the crumbs as long as possible by breaking the continuity of the protein starch structure. Puff pastry margarine. In puff pastry, it has to ensure that the many layers of the laminate stay separated. In the lamination process, whether hand or machine made, the thin layer of margarine must not break but has to adapt to the laminate in smooth, very thin layers. That is, it has to have high plasticity. Its C value is very high, up to 2600, and its melting point of 40 to 44 degrees centigrade is considerably higher than that of bakery margarine. Half-fat margarine. Most margarine laws allow for half-fat margarines with fat contents prescribed 40%. In such reduced fat products, the water phase has to be stabilized with thickeners because the emulsion and the crystal network alone are not able to guarantee temperature stability and good shelf life properties. So this was all about margarines, their structure, composition and properties. Hope you have understood it well. Thank you and have a nice day.